The foundational assumption powering modern language models is that meaning can be mapped. Specifically, it can be reduced to a single coordinate in a high-dimensional Euclidean vector space. Within this space, the mathematical engine is the dot product. It acts as a geometric flashlight, measuring directional alignment to ask a simple question. In a grouped cluster, we find related concepts positioned closely together, like dog, mammal, and pet. The model's attention mechanisms rely explicitly on this Euclidean proximity. When generating a sequence, the system uses these distances to weight which tokens are most relevant to the current context. This mathematical architecture is flawlessly optimized for capturing statistical associations across billions of text documents. But this statistical association is not actual reasoning. Equating statistical proximity with truth is a structural failure. It traps these models in a continuous semantic fog, allowing them to associate words fluently without ever grounding them in strict logic. Flat vector spaces structurally obliterate the precise characteristics that govern reality, like rigid hierarchies, explicit grammatical roles, and dynamic causality. This limitation mirrors Plato's cave. Dense embeddings are a low-dimensional projection of a highly complex reality. The model only sees the static, rigid shadow on the wall, not the shifting three-dimensional form casting it. The current approach to scaling models with more data and compute focuses on increasing the resolution of that shadow. It does not allow the system to observe the actual object. Escaping flat space does not require abandoning differentiable learning or the immense computational efficiency of the dot product. Linear algebra is highly adaptable. It natively thrives across richer mathematical objects, adapting easily to architectures that are curved, relational, and dynamic. To better model causal reasoning, AI architecture must project reality onto entirely new mathematical cave walls. The first major failure of flat space is its inability to embed exponentially branching hierarchies without extreme geometric distortion. Biological lineages, logical taxonomies, and conceptual abstractions naturally form tree-like structures, expanding outward at each successive depth layer. This diagram shows what happens when we force a sprawling biological taxonomy, like animal down to mammal, dog, and poodle, into a rigid 2D grid. The outer, more specific nodes are violently crushed together and overlap. We can solve this using a hyperbolic manifold, like this Poincare disk. Here, geometric volume expands exponentially as you move outward from the origin. The identical taxonomic tree now spaces out cleanly, center, and distributing specific concepts cleanly along the infinite periphery. The dot product survives here. We simply replace ordinary Euclidean similarity with Lorentzian inner products to measure hierarchical distance. When the architecture's geometry explicitly carries the hierarchy, the neural network no longer wastes parameter space attempting to memorize rigid taxonomic rules. The second major architectural flaw is the collapse of complex multilineal relationships into simple pairwise vector lists. Consider the strict causal difference between the sentences "dog bites man" and "man bites dog." Looking at these two data clusters representing those sentences as standard vector arrays, we see a complete loss of relational direction. The distinct semantic roles blur into an identical statistical soup. If we transform this representation into a structured 3D tensor grid, we lock the elements, subject, verb, and object, into strictly independent orthogonal axes. Meaning is no longer compressed into a single semantic point. It is stored as a multi-axis mathematical object that separates roles, relations, and contexts. The dot product functions here through tensor contractions, enabling generalized multilinear comparisons without data loss. Upgrading from vectors to tensors prevents language models from hallucinating causality by giving grammatical structure an explicit algebraic skeleton. The deepest flaw of modern embeddings is the assumption that every concept is a static noun, occupying a fixed location in memory. Logical functions, concepts like because, not, if, or even life, are not coordinates in a database. They are active transformations. Operator-based representation redefines meaning. Instead of defining a concept by where it sits, it is defined by how it directly alters a system's state. This diagram shows a static vector coordinate fading out, replaced by a matrix equation. Here, an operator transforms the initial state vector, sending it along a completely new trajectory line. Matrix math natively supports this approach because matrices themselves are engines of transformation. Zooming out into a complex phase space, we can map this operator logic into full dynamical systems. A conversation or reasoning chain becomes an evolving trajectory flowing into distinct, stable attractor basins. This mirrors biological intelligence. Reasoning is an active process of maintaining coherence far from equilibrium, continuously rejecting incoherent states. Causal logic requires moving beyond the storage of fixed coordinates towards systems that can represent dynamic state evolution. The dot product itself is not the limitation. The limitation is applying it exclusively to flat vectors. There is a vast toolkit of mathematical spaces that still utilize alignment scores to function. As we see in these simultaneous models, we can use tensor contractions to isolate grammatical structure, Lorentzian inner products to map strict hierarchy, and phase space matrix transformations to model dynamic state evolution. The central question for AI researchers is no longer how to measure mathematical alignment. The question is, what kind of reality is being aligned? The matrix machinery of AI is universal, but its future utility depends entirely on selecting the correct mathematical cave wall for the problem at hand. Relying on a single vector space is mistaking one shadow for the entire world. Future architectures could integrate these methods by using a dynamic inference layer to mediate between frozen weights and active logic. This functions like an epigenetic layer in biology, where a second system of activation regulates the expression of fixed DNA-like weights to bind roles and logic in real time. This integrated architecture forms a simulational world model, an engine designed to predict state transitions rather than next token probabilities. Logic becomes more grounded when we stop mapping the statistical shadows of language alone and begin to represent the multidimensional machinery that casts them.